So if you're walking in, please find a seat quickly so that we can start. That goes with you back there. Okay, so we're here coming very close to the end. We just have to cover one more chapter. Finish a little bit of the previous chapter. Forget which number it is. 7, I think. And then actually 6. And then, which is the one on entropy, and then finish with chapter 7, which is the one applying the second law of thermodynamics to a control volume. And in fact, I'm going to start with that because as I do that, we'll develop the last portion that we need to cover in the previous chapter. So we need to discuss the second law of thermodynamics as it applies to a control volume. Because most of the problems that are useful for us as engineers involve control volumes, meaning that there is mass that is crossing the boundary going into our control volume, into our system, or perhaps going out of it, or both. So let me step back and show you what we have from last time. We, as we were working with the second law for a control mass, we arrived at this expression, which you can consider as a mathematical expression for the second law of thermodynamics for a control mass or a closed system. It essentially tells you what the change in entropy is if you have a system that undergoes a process from an initial state 1 to a final state 2, then that equation would apply if you want to calculate, for example, the entropy change, delta S, for that control mass, for that system. It involves, obviously, the heat transfer term that we have been discussing, and it involves the entropy generation term that we discussed last time. It is actually difficult to calculate the entropy generation because it depends on several of the irreversibilities that we know can exist during a process. So it's very unlikely that you would use this equation to find the entropy change, assuming that you can somehow figure out what the entropy generation is. Most of the time you would find yourself using this equation to find the entropy generation because you're able to calculate the entropy change some other way. So, but we have it, if we have a system goes from 1 to 2, we can use that equation, and that delta S would be the change in entropy. And as we did with the first law of thermodynamics, we can also take this equation, and instead of writing it for the entire process from 1 to 2, we can write it in differential form if we just take a segment of that process path and calculate the entropy change, the infinitesimal entropy change during that segment of the total process. And we would just write the same equation, but we would write it in differential form. Of course, the integral would disappear. We would just have that. And then we would have a differential amount of entropy generation. Same equation, but now written for this infinitesimal segment of the total process. So let me put a little arrow here. So this applies to this. Notice how I write the delta entropy generation with the broken delta, just like I did for the heat transfer and the work earlier in the course, because it's also a quantity that is dependent on the path that you follow. The amount of entropy that a process generates depends on the process itself. So it belongs to those quantities that are not exact differentials. So work, heat transfer, and entropy generation, when we write them in differential form, we write it with the broken delta. Whereas the entropy is a property, and we write it with D. The differential quantity is an exact differential. So that's the same equation. So you can write maybe this, call this one differential. And then I can obtain what we call the rate form. If I'm interested now not in the infinitesimal change ds, but in the rate at which that change occurs, then I can divide by the infinitesimal amount of time that has elapsed during that infinitesimal portion of the process, and then I can write ds dt. Here I would have delta q over dt. We have seen that before. We have already encountered that. We call it q dot. This is the heat transfer rate. So this becomes q dot over t. And then now we encounter a delta S generation over dt. We appropriately call that S dot generation. So I can write this equation, which we would call the rate form of the expression for the second law. So there you have three ways in which you can write the second law, depending on what you are interested in. All right. So, and this is actually what we need. That's the last part of this chapter in entropy. It's just the derivation of this equation in rate form, but it's immediately preceding what we need to do next, which is to develop an equation for a control volume. This was for a control mass. In fact, we can, to make sure that we don't get confused, we can put here Cm, so that we're applying this to a system that looks like that, where there is no mass crossing the boundary. Make a note there. Control mass, no mass crossing boundary. So what we want to do next is, well, let's change the system to one in which mass can cross the boundary. So change the cartoon to a control volume. Leave that there. If I now have a control volume, and there is mass coming in and mass perhaps exiting, then how do I modify the equation right above for this situation? And the modification is actually very easy, because it's simpler than the one we had to introduce when we were looking at the first law, and we had to modify the first law that we had obtained for a control mass, modified for a control volume. We had that additional work term called the flow work. In this case, we don't have such a thing. So if mass comes into the system, with respect to this equation, what does that mass carry in with it? It carries entropy. It carries, in fact, any property that is associated with that mass that is coming in. But since we're talking about this equation, then the only thing we have to worry about is that it carries in entropy. So it's very easy then. How do I find the rate at which entropy is coming in with that mass? If I have them in terms of rates, which is the way I have written the equation, you may want to add dots there, because we're having it in terms of rates. We have certain amount of kilograms per second coming in, certain amount of kilograms per second going out. Then all we need to do to this equation is add two terms on the right-hand side. What do we need to add? Incoming mass rate times what? Per unit mass. So let's call it lowercase SI. That would be the entropy per kilogram that is coming in with that mass. That is positive. It gets added to my system. So remember, I'm adding to this equation. And of course, if any mass leaves the system, then it takes away minus m dot E SE. And that's all. That's all I need to add to our expression of the second law if we want to apply it to a control volume. So the full equation is, let's write it again because we want to change the notation here. Now this is not for a control mass, but for a control volume. Everything else I'm just copying, so Q dot T, rate of entropy generation, MISI, M dot E, SE. That's our second law for a control volume. So now we can apply this equation to problems involving control volumes. And we have already seen devices where we can apply this law. Any device that we have seen before that has flow in, flow out, turbine, compressor, a boiler, a condenser, an evaporator, any of the devices, a nozzle that we have seen before where there is mass flowing in or mass flowing out, we now have an equation that we can use to help us solve the problem involving that device. Just like we did for the first law, we're going to consider two types of problems that are important for us. So let's write here two types of problems. Does anybody remember what two types of problems we examined in connection to the first law when we applied it to a control volume?
Steady state.
There were some steady state problems and two, or transient. If it's not steady, it's transient. So we're going to do exactly the same thing. So we'll look at some steady state processes, and we will look at some transient processes. And it's just because for each one of these two, the equation can be simplified somewhat, or changed. In the case of the transient problem, we'll have to change the equation a little bit. Okay, for the easiest one are the steady state problems. So if we're looking at a steady state problem, what do we mean? Here's the equation. What can I simplify in the equation if it's a steady state problem? If it's a steady state problem, it means that if I look at the control volume for a period of time, I always see the same thing. So there are no changes in the properties in my control volume with time, right? So no time variation. So if I look at this equation, then of course I can say that ds dt in the control volume is 0. So if I take this equation, I just write it again with a 0 on the left-hand side. So let's do that. We get 0 equals Q dot over T S generation same equation, but with a big 0 on the left-hand side. There are many situations, most of the problems that you have done, in which your device, let's sketch it as a black box, only has one inlet and one outlet. So one inlet, one outlet. MI, ME. What happens in that case if we are in steady state? ME equals MI, right? So in steady state, ME equals MI, and therefore we don't really need the subscript anymore. We can just call it M dot. That's the flow rate, the mass flow rate that is going through the device. It's the same at all times. And if that's the case, I can simplify the equation a little bit more because I can factor out the M dot I and the M dot E that appear there is the same. And I can rewrite the equation like this. I can write, move these two terms to the other side and divide by M dot. So SE minus SI is equal to, I'm now going to divide by M dot. So what is Q dot over M dot? Small q. And capital S dot generation divided by M dot is lowercase s generation. That's the generation of entropy per unit mass. So this equation is now per unit mass. It's a useful equation because if I wanted to, and if I could find the entropy change from the beginning, from the mass that is entering the device, it has a certain entropy. The mass that leaves the device, it has a different entropy. I can find the difference, outlet minus inlet entropy. If I know everything that appears on the right-hand side, I would have to know the heat transfer rate per unit mass. I need to know the temperature. The system is at its steady state, so it doesn't change with time. And then this is the tough one. This would always be difficult. So like I said earlier for the previous equations, most likely you would find yourself using this equation to find the entropy generation. Except in one situation, which is what happens if we have a process that is reversible, which is known as an idealization. If a process is reversible, then what happens? If a process is reversible, there is no entropy generation. So if a process is reversible, then S generation is 0. Or another thing that would be nice, and happens many times, if a process is adiabatic, then what happens? Q is 0. And if a process is both reversible and adiabatic, then what happens? If both, then of course S exit equals S inlet. So the entropy of the flow that comes in would be exactly the same as the entropy of the flow that comes out, because there is no heat transfer and the process is reversible. So those would be useful results if we use these equations. Let's see, I think I have an example, so we can use this. But let me see if anybody has a question. Okay, so let's just do a very simple example using this. So this is problem 7-100 in your text. So it's still from chapter 7. Okay, so what we have is a condenser. And so let's do a little schematic of our condenser. There is an inlet, outlet, and there is some cooling water. So let's say that this is the cooling water. All right. And we know this flow rate. Let me write it here as an m dot E, but it's the same as m dot I. 5 kilograms per second. So we know how much water is going into the condenser. That's the water that we are condensing. There is two inlets and two outlets, but they are separate. So if I'm just looking at my condensing water, then there is one inlet and one outlet. And that's the 5 kilograms per second. And we know that at the inlet, we have wet steam. So it has a quality of 15%. No, I'm sorry. A quality of 90%. 90% quality. And it is at 15 kilopascals. And when it exits as saturated liquid. All right. And the condenser is isobaric. So let's put that here somewhere. All right. Okay, and we are to find the heat transfer out. So how much heat is taken away by the cooling water? Q dot out. And to find entropy generation rate, if any. All right? Okay, so it's a very simple problem. There's nothing really too complicated. It's a steady state problem, so this condenser is operating continuously in steady state. And we're going to neglect any other form of energy that is not internal energy. So only internal energy when we look at the first law. Okay, perhaps even though they don't ask us to do that, as I always recommend, it might be a good idea to look at a plot on a convenient diagram. For example, in this case, we could do, obviously the pressure is given and is isobaric, so it would make sense to put pressure here. And here we really have a choice. We could put volume, which is what we would have done up to this point, but since we started working with entropy, it might make sense to put entropy per unit mass on the horizontal axis. So here, if I sketch the process, it's very simple. What is the process on this diagram? Since it's talking about quality and saturated liquid and so on, it might make a lot of sense to put the dome. And since we start out at 90% quality, we know we are starting out somewhere here. Right? This is our 1. And where do we end? It's isobaric, 15 kilopascals. So it has to be a horizontal line that ends at saturated liquid, right? Because they tell us that it ends at saturated liquid. So that's 2. That's the process undergone by the steam as it goes through the condenser. All right? Okay, so first law of thermodynamics. We want to write it in rate form and we want to write it for steady state. So since it's steady state, the rate form of the equation will have a 0 on the left-hand side. That will be the term that has the change in internal energy per unit time inside the control volume. That's 0. And then, of course, here we have Q dot, W dot, and then since there is mass flowing in, but it's the same, in and out, I'll just call it M dot. And then I can write HI minus HE. That's my first law for the problem. The work, or the power, the rate of work is 0. This is a condenser. And here what I have is an equation that immediately tells me what Q dot is M dot. And then if I move it to the other side, HE minus HI. M dot was given, and H sub E and H sub I you can find easily, right? For H sub I mean, I call them here 1 and 2, but I think to be proper, you want to switch that I to an E and these two to an E, but it's a minor thing. But just to have consistency in the notation, I and E instead of 1 and 2. But I can calculate both. In fact, H sub E is none other than HF, right, at 15 kilopascals. And HI I can get using the quality, right? Since I have the quality, I can get HI. So that's straightforward. I can give you the numbers. If you do that, you find HE to be, that's the one that is HF. So that's 225.9 kilojoules per kilogram. And H sub I, using the quality, will be 2361.7 kilojoules per kilogram. So I can plug that in, multiply times M dot, which was given. It was the 5 kilograms per second, and I can get Q dot. So I get Q dot. It will come out to be negative 10,679 kilowatts. That's the rate at which heat is being removed from the water that is condensing. I verify that I get a negative sign, so it's out, as expected. It's negative, so that answers the first question, the Q dot out. And the second question is to find the entropy generation. And how do we find the entropy generation? Well, we just developed this equation right here. So I can go ahead and take that equation and solve for the entropy generation. This is per unit mass, so all I need to do is multiply times the mass flow rate. But let's go ahead and write it down then. Multiplying times M dot, then we get S generation dot is equal M dot SE minus SI minus Q times M dot will be capital Q dot over T. So I just put that equation there and verify that I have everything I need to do that calculation. So M dot was given. I can read S sub what I need for S sub E and S sub I. S sub E again is an SF. So S sub E is SF at 15 kilopascals. And that number is 0.7548 kilojoules per kilogram Kelvin. And the S sub I, using the quality, is SF plus X SFG, also at 15 kilopascals. And that is 7.283 kilojoules. Oops. I did this once, didn't I? Back. I have to go brute force. Kilojoules per kilogram Kelvin. So let's wait until that comes up. Okay, so I can get that. So now I have everything because I computed the Q dot. And what is this temperature? Think about this problem for a second, and we'll just have a little bit of a discussion about this temperature. If you go back to the sketch, and even our diagram here, the condensing water is very easy because it's at a constant temperature. It's cooling. I mean, it's not cooling. It's just turning the steam into the vapor into liquid. All of it is liquid, but it's all happening at the same temperature because it's at a constant pressure inside the dome. That temperature, which you can also read in the table, is 54 Celsius. Okay, that's the temperature that corresponds to 15. Let me just write right here. T sat is 54 Celsius. So, but the cooling water will have to be at what temperature? This cooling water that comes in and out, what temperature would it have to be at? Huh? I'm sorry? Less than 54, right? Otherwise, there wouldn't be any heat transfer. So there would have to be some significant delta T between the condensing water, which is at 54, and the cooling water. And the larger that delta T, the faster that heat transfer takes place. But you might remember that heat transfer through a temperature difference, the temperature difference is a source of what? Entropy? Yeah. It's a source of entropy because it's a source of irreversibilities. For this process to be completely irreversible, the cooling water temperature would have to be only an infinitesimal amount less than the 54. Infinitesimal. If it's an infinitesimal amount lower than the 54, then that heat transfer takes place in a quasi-steady manner because there's only an infinitesimal temperature difference. But you would need a very large surface area to be able to accomplish anything significant. So as you can see, there is a compromise between getting things done quickly and generating entropy or making the process irreversible. If you make the assumption that the delta T is only infinitesimal, then of course that means that it's only infinitesimally smaller than 54 Celsius. You can use the 54 Celsius. Remember that you have to convert it to Kelvin. So this is, I'm just in that equation, the 5 kilograms per second mass flow rate, SE and SI, which we just got here, minus 7.283. These are kilojoules per kilogram Kelvin. And then minus Q dot over T. Remember, the Q dot was negative. It's a little higher because it was out. You have to make sure you take care of the sign. It's minus Q dot, but Q dot is negative. So this will come out to be positive. The Q dot that we found before this drops again The Q dot that we found was 10,679 kilowatts. And the temperature, if I am assuming that it's only infinitesimally small, will be 54. You have to put it in Kelvin, so 273. And that's in Kelvin. And then you can do the numbers. What do you think the numbers come out? What do you think that number comes out at? Should be zero. And if you do it, you'll get zero. If you get a little bit different than zero, you can put the 273.15 if you want to make this a little bit more accurate. But this will come out to be zero. Because in fact, by making the assumption that the heat transfer takes place only through an infinitesimal temperature difference, where in fact, that would be the only source of irreversibility that we have. If the process is reversible and there is no heat generation. But like I said, in reality, there would have to be a delta T, and that would translate into this temperature having to be lower than 54 Celsius. If that temperature is lower than 54 Celsius, what happens? This denominator would be a smaller number, and therefore this quantity, which is positive, will be larger. So in reality, the T is less. The typical temperature across which the heat transfer takes place is less, and S generation is positive. And then the number that you get will directly depend on what temperature you use in that equation. So there is a little bit of ambiguity as to what it is, because you can imagine that the temperature of the cooling water will change. I think the actual statement of the problem says that the cooling water is at, I think it is 17 Celsius. I on purpose didn't give you that number at the beginning, but it's in the statement of the problem. It says the cooling water comes in at 17 Celsius. Obviously, it'll have to come out a little warmer because it's taking heat from the condensing water. But it says to use 17. So if you plug 17 plus 273, then you get a positive number for the entropy generation. But I think it's better to show you this little nuance about when does entropy generation happen and why in this problem. It's because of that. Okay, any questions? All right, so let's get that here. Okay, if we have time, I'll do another problem using this steady flow. But there's obviously many problems that you can solve. I just did this one for the condenser, but you can do turbines, compressors, pumps, etc. But let's actually look first, before we do any other problems, at the other possibility, the other type of problem that we can encounter. So go back to this. We did that. Know how to do steady state problems. Now we want to do transient problems. The typical transient problem that we saw before was, for example, when a tank was being filled. So if I had, for example, a line and then a tank or a container that gets filled by opening that valve. And if I look at what's happening inside that container as it gets filled, then that's a transient problem. Because if I now look at this control volume, and I look at it at different times, it doesn't look the same at different times. It's more fluid in as time passes until the process ends. So in order for us to have an equation that is useful for those problems, we need to go back to this. So we go back to this equation. which is the complete equation. The second law for a control volume. But we want to modify this equation a little bit so that we can use it for a problem such as the filling of a tank. What we need to do first, in fact, is undo some of the things that we did to arrive at this equation. You remember the way I arrived at this equation was by starting from this form of the equation, and then I wrote it as a differential form, and then I divided by the dt, so I got a rate form. Now I'm going to kind of go back because I'm going to take this equation and I'm going to integrate it in time from the beginning to the end of the process. So if 1 is the initial state and 2 is the final state, then what I want to do is I want to take this equation and integrate it. Multiply times dt. Let's leave this equation here so we can see it. Multiply times dt and integrate it. Clearly, some of the terms are going to give me what I had at the beginning. But let's see what happens exactly. So if I take that equation and multiply times dt, I get ds equals q dot dt over t, s dot generation dt, m dot I si dt, minus, I'll write it underneath, m dot E se dt. I have that. Multiply times dt. And now go ahead and integrate between 1 and 2. All right, go ahead and integrate between 1 and 2. Obviously, this becomes delta S again, right? The integral of ds between 1 and 2. This q dot was delta q over dt. So this goes back to what it was before. I can cross out the dt, and this becomes the integral from 1 to 2 of delta q over t. That term goes back to what it was initially. And the integral of s generation dot dt from 1 to 2 gives me the total entropy generation between 1 and 2. That's what I had before. So, but now these terms become the integral from 1 to 2 of m dot I si dt minus the integral from 1 to 2 m dot E se dt. So these are the new terms. And so what happens from this point on depends on any assumptions that we make about the incoming and outgoing masses. So remember, the generic problem is like this. It's a control volume. Something coming in, something coming out. If this is a filling tank problem, obviously there is nothing coming out. There's only something coming in. But in general, there could be either. So I have an integral. This integral can become trivial if I make an assumption. What do you think the assumption would be? Huh? No, that would be too trivial. I don't want to eliminate the mass. So if I have mass coming in, mass coming out, those are the rates, m dot I and m dot E. But how can I make these integrals trivial? Not zero, but easier to calculate. If I assume what? No, it doesn't have to do with m dot, in fact. The entropy, right? This is the entropy of the flow or the fluid that is coming in, or if this happens to have, suppose it has a hole here, and there is a leak, right? There's stuff coming out, so that it's not zero. But that's the entropy of the fluid coming in and the entropy of the fluid going out. If I make the assumption that those quantities, Si and Se, do not change in time, right? Right? If I make the assumption that Si and Se do not change in time, what happens to those integrals? What happens to this integral? To the first integral? If Si doesn't change in time, why would it be 0? Huh?
It's just times delta t.
The integral of what?
So it'll be m dot I si delta t from 2 to 1.
No, that's not exactly right. Let's all agree that the Si is a constant. I don't have to integrate it in time. It comes out, right? So that first integral becomes, I'll do it down here. That first integral from 1 to 2 becomes this, right? And what is that integral? What is the integral of m dot I dt from beginning to end? In fact, Si is there. All you have to do is tell me what the integral boils down to. The integral of the mass flow rate per time. MI. Right? Integrating the mass flow rate per unit time over time, you get the total mass, right? MI. So, and the other one, of course, becomes SEME, right? So the equation becomes, if we make that assumption, you might argue it's trivial. I could have said that from the beginning. But it requires that assumption because we started with a rate equation and we're integrating it in time. But if we don't make that assumption, it could be complicated. The problem could be complicated. And in fact, I won't give you a problem where you cannot make the assumption. So in fact, that will be your workhorse because you can make that assumption for this type of problems. So that's what we have. Now, you still have another integral here, which could be difficult because the only way that you can resolve this one is if you know how the temperature is changing during the process. In fact, you have to know how the temperature changes with respect to the heat addition process or heat rejection, depending on where the heat is. But that's complicated unless the problem happens to be isothermal. If the problem happens to be isothermal, then that temperature can come out. But in general, it's better to leave it in there because we don't know. So that's then the equation that we would use for a problem like this. So let's, in fact, treat a problem like that. So it's the same problem. So except I will plug this. I'll put a big plug there. There is nothing coming out. So we're going to look at the filling of a tank or a container like that one. Let me get you the numbers. So the numbers that we need are the volume of this container is going to be 0.2 cubic meters. It's initially empty, so state 1, let's put it right here, empty. Okay, for this problem. And what is flowing through this line is CO2. Then this CO2 is at 3 megapascals. And it's at 60 Celsius. That's the CO2 that is flowing through there. So the container is empty. Then I will open the valve. So final state is full. Okay? When the tank is full. I'll put it in quotes. When it's full. And to make our life very easy, we're going to insulate this whole thing. So it's all insulated. Insulated. All right? So that's the problem statement. And then you need to find the final temperature and if there is any entropy generation. So let's do it here. Okay, so find T2 and entropy generation. Okay? That's our problem. Okay, so essentially a problem like this, you should think of 3 conservation laws or 3 equations. We call them conservation laws in general. What's the first one, the simplest conservation law that you have to worry about? Mass conservation. So if I write mass conservation for this problem, what do I know? What is M1? 0 because it's empty, right? And what is M2? Min. That's what I wanted to hear. M2 has to be Mi, right? That's our conservation of mass statement. Final mass is the mass that comes in. If we had had some initial mass, then of course there would be a difference, right? M2 minus M1. So that's our first conservation law. What's the next conservation law that we have to worry about? Energy, or another name, first law of thermodynamics. Okay? So we write it. We have it somewhere, so we bring it over here. Yeah. Right? And then right? And there is no ME, right? There is no exit in mass. So that's the form of the first law of thermodynamics that we learned when we looked at the first law of thermodynamics for a control volume. Neglecting kinetic energy, potential energy variations, so that all the energy is really internal energy. Okay, so what can I do here with this equation? Can I simplify it? Delta U, of course, is U2 minus U1. What's Q? 0, because it's insulated. Work? 0 is a rigid tank. And what's capital U1? 0, because there is nothing in there initially. And what's capital U2? M2 lowercase u2. So this is the first law. Right? And because we have our conservation of mass statement that we just made right above, we can simplify this, right? This is the same as that. So the first law of thermodynamics gives me that. An interesting result. U2, the internal energy per unit mass of the CO2 inside the tank at the end of the process is equal to the enthalpy of the CO2 that is coming in from the line. Right? Okay. Can I answer anything at this point? We were asked for did I tell you what yeah, I guess, what did I say? The final temperature, I don't know if I wrote it anywhere. Oh yeah, it's right here. Find temperature at the end and entropy generation. So can we find this temperature at the end of the process? CO2. That happens to be one of the substances that you have a table for, a full table. So if you go Appendix B, it should be B3. Yeah, so B3 has CO2, saturated carbon dioxide. So that's, we have that. So we can go to this table and enter it at the pressure and temperature of the line, which was 3 megapascals, 60 Celsius. So more than likely, that's going to be superheated. Let's see, 3,000. Okay, so it's a superheated value. Uh, 3,000 kilopascals, saturation temperature minus 5 Celsius, but we are at 60, so it's superheated. But we can come in here and read whatever we need. You know, we have the specific volume, internal energy, enthalpy, and entropy. In particular, I really need the enthalpy, because I have it here that I needed. Yeah. So I can read HI. What was it? B32. And read my H sub I. If I read that number, it is 400.2 kilojoules per kilogram. And I'll read also the entropy. I'll read SI. And that's going to be 1.477 kilojoules per kilogram Kelvin. Get those two values. So first law of thermodynamics tells me that U2 is HI. So I know then that U2 is same as HI. So 400.2 kilojoules per kilogram. So I know that about the final state. What else do I know about the final state?
Temperature now?
Do I know the temperature?
You can just look it up
How?
with U2.
Okay. Can I look it up with you too? Give you the book. You need to know another property, right? You need to know another property. So, do I have another property? I was going to check if we also have in the ideal gas tables. Because, you know, you could, it's superheated. So you could say, well, if I don't have anything, I can treat it as an ideal gas. So, we have, we actually have CO2 as an ideal gas. Let me see. So you could do that if you were to assume that it is an ideal gas. Remember, for an ideal gas, the internal energy is only a function of the temperature. So since you have the internal energy, then you could back out the temperature. Yes. Find this, but at what? You'll have several values that have 400, depending on the pressure and the temperature. The answer, the key to the answer, is in the statement full. When is it full? When it reaches the same pressure. Because if I open that valve, there's going to be a flow from the line, which is at 3 megapascals, right, until the pressure equalizes. Right? So once the pressure equalizes, then obviously there's no more than can flow in. So I can do that. I can go to at the same pressure, find the temperature that gives me that U, and let's see if we can do it here. So 400.2, here's the same table that I was just looking at. At 3,000 kilopascals, right? I read the value at 60 Celsius. Right? That's what I read the H of 400.19. All I need to do is find that number, but in the column of U, right? So it will be somewhere between these two, between 120 and 140 if I do an interpolation, right? 120 and 140. So if you do the interpolation, what did I say? 120 Celsius. 140 Celsius interpolation for U2, then you find that I don't think I have the number. I don't have the number, so you can, it'll be, well, we can eyeball it. What is it? 400. Just do 400. Where's the number? Oh, 400. Let's just do 400. So 392, there's 8. It's right about in the middle, because this is 392 and this is 408. So I would say with a lot of confidence about 130. Okay. So T2 is about 130 Celsius. All right. Okay, I was going to check one thing here. You can do it on your own, I guess. You can redo the problem making the assumption that it is an ideal gas, right? And see what you get. So redo if CO2 in line is treated as an ideal gas. Right. You'll get probably a very similar number. You will only be run into problems if some of the CO2 is liquid, so then you have a mixture, and then of course it wouldn't make sense if you have a mixture of liquid and vapor to assume that it is an ideal gas. Okay, but we haven't finished. We have to do the entropy generation. So to finish the problem, I just have to, again, use this equation that we developed here. We actually have a better version of it right here. That equation to find the entropy generation. Right? So if we write this equation, the delta S is S2 minus S1. So that's our final law, second law. I'll find a conservation equation. So we would write S2 minus S1 is equal, there is no heat transfer, it's insulated, so that's 0. Entropy generation, all right? And then MI SI, and there is nothing exiting, right? So that's all I have. And then there is no S1, it was initially empty. And S2 is M2 lowercase s2. So that's entropy generation plus MI SI. Of course, MI was the same as M2. So I can just simply write this, that entropy generation is M2 times S2 minus Si. Okay? And that completes the problem. How do I find M2? Well, let's say we're using the full table, not the ideal gas table. Using the full table, like, because that's the way I was doing the problem. I can just read the specific volume, right? So I can read V at the final temperature, which is this 130. And now that I have the specific volume, since I was given the volume of the container, the 0.2 cubic meters, then I can find M2 as V over V2. Right? I can get that M2. SI, I read it earlier in the table. So SI was 1.477 kilojoules per kilogram Kelvin. And I can just go back and read S2 in the same table so read S2 at T2. Of course, it's T2P2. So I can read that, and then I can get this number. And in this case, you won't get 0. You will actually get entropy generation. You should verify that it's a number that is greater than 0. Mm-hmm. Okay, let me see here. Oh, wow. Does anybody have a question? No questions? I do have questions. So let's finish by doing semi-clicker questions. Okay, so ready? First question is right there. For a process to be isentropic, it must be A, reversible, B, adiabatic, C, reversible and adiabatic, D, reversible or adiabatic, and E, none of the above. That's actually in today's lecture. 5, 4, you already have no clicker?
I didn't remember that.
You're going to miss these easy points. Okay, closing it. Today's lecture. Okay, yeah, most of you are paying attention. It has to be both, right? Reversible and adiabatic, right? Just look at the equations today. The equation that we wrote for the change in entropy, it has the heat transfer term and it has the entropy generation term. All right, another one. For a Carnot heat pump cycle, the cyclic integral of delta Q over T is equal to 0, greater than 0, less than 0, or none of the above. And you can punch in. All right? 5, 4, 3, 2, 1, 0. And the answer is correct, equal to 0. Right? The key word right there is Carnot, right? Because Carnot is reversible, is ideal. And if you look at the Clausius inequality, which is what that integral is, the Clausius inequality is less than or equal to 0, is never greater than 0, And it's less than 0 for any real cycle, but this is an ideal cycle. One more. The specific heat ratio, K, for air at standard conditions is about 0.7, about 1, about 1.2, or about 1.4. 5, 4, 3, 2, 1, 0. Okay, very good. See you next time.